Hey y'all, happy Wednesday. Hope you guys are doing well and that the quiz went well yesterday. I will get that graded as soon as I can and get it back in the folder so you guys can take a look at how you're doing. Today we are going to look at chemical reactions involving gases and how can we do some calculations that involve gases. And so to kind of kick this off, we're going to watch this short video to kind of look at a chemical reaction that involves gases and how we can use that to kind of end our discussion. So let's watch the video.
In this demonstration, we're going to observe some properties of chemical reactions. In the 5 flasks in front of me, we have 1 molar concentrations of acetic acid, and there's going to be equal volumes of each in the 5 flasks. In the balloons on top of the flasks are 4, 8, 16, 32, and 64 grams of sodium bicarbonate. This reaction is the classic vinegar baking soda reaction that's going to produce a gas. So we're going to collect the gas on top of the balloon and we're going to compare the relative amounts. So as I dump the sodium bicarbonate into each container, we can see that as we add 4, 8, and 16 grams of the sodium bicarbonate, the balloons are going to be different sizes. So as we can see, after this reaction completes, we roughly have double volume going from 4 to 8 and then from 8 to 16 grams for this particular reaction.
So let's talk about what's going on. So what if I ask you, okay, well, what was the actual volume in the first balloon of gases that he collected? Remember, he put in our 4.0 grams of our sodium hydrogen carbonate, right? So sodium bicarbonate. And I want to know, well, how much gas he collected in that particular balloon. And how would we do that calculation? Well, to know that, we need to know what's going on inside the room. And so let's just say inside the room that the temperature was 25.0 degrees C, and we'll make it easy on ourselves and let's say that it was 1.0 atm in terms of atmospheric pressure there. And so you can see on the board behind him that he has the reaction written down, but I'm going to rewrite it again. He said that they used some acetic acid, and let's get acetic acid right. It's HC2H3O2, and they reacted that with our sodium hydrogen carbonate, and that produced our sodium acetate. And since we are reacting an acid plus a hydrogen carbonate, we're going to produce CO2 plus H2O. And the question becomes, well, how much of the CO2 was actually collected? And I want to know how many liters of that CO2 was collected. How big was that balloon after the reaction for that 4 grams? And so we're going to have our 4.0 grams, and for this particular reaction, the acetic acid is in excess. So how do we do this? Well, the first thing that we're going to have to do is we're going to start with our 4 grams, right? And so we're going to start with our 4.0 grams of our NaHCO3, and we know we're going to convert that into moles. So for every 1 mole, we have 84.01 grams, and we get 0.0476 moles of our NaHCO3, right? But we won't want that. We want CO2, so we know that we have 0.0476 moles of our NaHCO3. Mole ratio is pretty easy in this case. For every 1 mole, so you get CO2, we get 1 mole of that reacted. And that means that we get 0.0476 moles of CO2 produced in the reaction. Now the question is, what do we do with that? And I'm going to move over here and say, okay, well, we don't want grams, right? We want to know what liters is. And so, well, we have a moles of gas at a certain temperature and pressure. We have it right here. And so how do we do this? Well, hopefully now you remember that if we're looking for the volume of a gas at a particular temperature and pressure, we can use PV equals nRT. In this case, we want the volume, so I'm going to rearrange it to be V equals nRT over P. And lo and behold, we already have this. We have our temperature, we have our pressure, and hopefully you remember that R is 0.0821 liters atmospheres per mole Kelvin. Right? And so now it's a matter of plugging and chugging, making sure that we're in the right units. We already have moles, right? So we're going to say we have our 0.0476 moles of CO2. And I'm just going to get rid of that because it's going to get in the way, right? Times our 0.0821, which is R, times our temperature. Remember, our temperature needs to be in Kelvin. So if we were at 25 degrees here, we need to be in Kelvin at 298. And that's all going to be divided by 1 ATM. And so if we look at that answer would be 1.16 liters. So in theory, that balloon would be 1.16 liters. My guess is that it's going to be a little bit less than that because gas is seeping out and the balloon won't expand that much, right? And we saw in the video that, okay, well, that hopefully makes sense, right? And we see in the video, well, number 2, when we put in, we have 4.0 grams. We know we get that 0.0476 moles of CO2, and that resulted in a volume of 1.16 liters. And he said, well, the 8 grams that he put in was a little bit bigger. Well, that should make sense because we doubled the mass, which means that we double the moles, right? And if the temperature and pressure stays the same, then we know, according to Avogadro's law, that we should then double the volume. And again, we doubled here, 16.0 grams, right? And we have 0.190 moles of CO2 there. So we doubled that, and if we doubled that, keeping the temperature and pressure the same, we should get to the 4.64 liters. And again, this all assumes that my acetic acid was in excess, which it was in those first 3 balloons. Okay, so we can use stoichiometry, and then we can incorporate the ideal gas law to figure out a volume, as long as we have a temperature and pressure. So let's look at another example, right? And so in this particular example, we see butane undergoes combustion reaction when it reacts with oxygen gas to produce carbon dioxide and water. How many grams of butane would need to react with 6.75 liters of oxygen gas at 18.6 degrees C and 835 millimeters of mercury? Well, to save us some time, we have a balanced equation, right? And then we have this little thing because fire is good, right? Don't get excited, Dylan. You're still not allowed to play with matches, but fire is good, right? And this is basically a butane lighter, so we know that, hey, butane's going to be in there. And so let's get rid of our little Giphy here so we don't sit there and stare at it forever. Right. Sorry, Dylan. And so if we look at this again, right, now we have a certain amount of CO or oxygen. So we got 6.75 liters at 18.6 degrees C and 835 millimeters of mercury. And we want to know how many grams of butane we can burn when we kind of react all of that, right? And so again, we have a volume of gas at a certain temperature and pressure, and we're looking for grams. Now, first thing we got to do, when in doubt, go to moles, and we know how to get to moles because if we have a volume of gas at a certain temperature and pressure, again, we're going to use PV equals nRT, where N equals PV divided by RT. And so, again, we have a pressure and a volume and a temperature. Now, volume's okay. We know that we have to convert this plus 273, right? And so we're going to get 291.3 Kelvin. And we also have that, but we had to divide that by 760, and that's going to be 1.099 ATM. Okay, and now we can just plug and chug. And so let's say, okay, well, we have N, that's going to be equal to my pressure, which is 1.099 times my 6.75 liters, all over R, again, is 0.0821 times my temperature, which is 291.3. And that's going to give me 0.310 moles of O2 that needs to be reacted. So now that we know the number of O2, moles of O2, then we're just kind of back into it. Now we know moles of O2. Then we go 0.310 moles of O2 times my mole ratio, which is in this case 2 moles of C4H10 divided by 13 moles of CO2. Which is 0.0477 moles of C4H10. And then if we want to know grams, obviously we can multiply that by the molar mass, 0.0477 moles times, for every 1 mole, we would have 58.14 grams, and that's going to give me a gram whopping total of 2.77 grams of butane that I could react with this much oxygen gas under those conditions. Okay, so again, we're just using the ideal gas law to get us into or out of our mole map and kind of finding out what our answer should be. Okay, so work on the practice problems, answer the questions from the assessment, the daily task in the assessment file, and reach out if you have any questions, okay? All right, guys, peace, love, happiness. Thanks for playing.